Hi there, I'm Daniel Galvez. I'm an engineer who's been working with MLCommons for a little over a year now. And what I want to share with you is some in the weeds learnings about how you can effectively use Apache Spark with, in this case, TPUs, but in general, uh, machine learning accelerators, especially for deep learning, for offline inference use cases, in particular on sequence data. So if you're interested in sequence data and offline inference with accelerators in your data engineering pipelines, I think you'll find at least some bits of this talk interesting. Uh, I'm required to have this slide, but this is my first time giving a talk to such a wide audience. So if you do have any feedback, I would really appreciate it, other than just Databricks themselves. So please do that if you get a chance. So we have a few topics, but let's just dive right in. So the data set I'm going to discuss, which is a speech recognition data set, it was worked on via MLCommons. And MLCommons is perhaps a name familiar to some of you, but probably MLPerf is better known. And MLPerf essentially is today probably the best in the sense that it's most complete and least biased deep learning training and inference benchmarks for various hardware and software systems. You can see results on various setups of like say TPUs, GPUs, and other accelerator systems and hardware setups. Rotary has an Excel spreadsheet, and like it. A lot of you may know it's very hard to get numbers, concrete numbers on these sorts of things. But I won't talk too much about MLCommons. If you want to know more about it, the executive director, David Cantor, is actually going to be speaking, at least when I made these slides, on Thursday at 4:25 p.m. So if you might want to know more, I suggest you go to his talk. But the reason why it changed its name from MLPerf to MLCommons is that they recognize that just doing benchmarking, there's actually a need. So benchmarking is difficult because there's a lot of moving variables among different setups. And a way to make benchmarking easier is you expand into what they call machine learning best practices, which people vaguely know as MLOps, as well as creation of data sets, which is what I'll be talking about today. At least one specific instance of data set development anyhow. So I won't talk too much about what exactly the people speech data set is, because this is really an engineering talk to help data engineers understand some of the issues I face, and hopefully I can help them out with their own work. But just to give some context, the people speech dataset is a speech to text dataset. So it's designed to train things like, like Siri and the Google Assistant and so on, or just automatic transcription services. And one of the things we found, one of the things that MLCommons in general has found is that it's actually quite difficult to get a good benchmark data set for a couple of reasons. And those three reasons are best summarized as the following. A data set needs to be challenging, so it needs to push the state of the art. If a data set is too easy, then you can't really have a good training benchmark, because if everyone's getting like below 2% word error rate on a data set, like humans have a word error rate, which is how many mistakes we made while listening to people speak, of 5 to 6% word error rate or so. So once you go beyond like superhuman speech recognition on a particular data set, it's probably too easy. And I'd say like the most common data set today, at least in speech, is LibreSpeech, which does have the next property, which is that's free as in bear, as in you can just get it and you have it, which is very nice if say you're not a speech to text expert, say you're just a machine learning person, but you develop a new model or a new training mechanism, and you decide, I want to see how this does on speech data. If you have to buy a data set, buy a speech data set, those often run something like 10 to 20K at the high end. And if you're a student, or even if you're like a professor or postdoc or whatever, it can actually be quite hard to justify those sorts of expenses. So you would like a data set to be free for the sake of our academic friends, so that they can just use it easily. And finally, you want a commercial uses license, and that's for the friends on the industry side. So on the industry side, it's usually acceptable to use, according to American copyright law, it's acceptable to use any data you want for what's called research purposes. But in industry, it's very hard to distinguish between research and development and business, especially if you're a research and development company, which honestly applies to a lot of companies doing machine learning and data science today. So you really want a commercial usage license. And I don't want to talk too much about this, but the way you get that from data, which is scraped off the internet, scrape is perhaps the incorrect word in this case, download off the internet, is that you essentially need to check that it's either public domain or covered under the so-called CC BY or Creative Commons by license. Works in under these two categories are generally accepted as okay to use in a machine learning data set. For reasons I won't get into. But you can automatically detect those sorts of things actually in the HTML tags of web pages. And that's actually how we got the underlying data of the people speech data set. The pie chart to the right, basically it shows that even in industry, most research papers actually use public data sets. And that's because even though you may have a big group inside your company doing, say speech recognition research, if you want to communicate outside your company, you can't use your internal data sets. So even within industry, there's a big bias towards open public data sets. So anyway, but let's get to the meat of the talk, which is I want to discuss what this workload is, what the offline inference workload I'm doing is, and all the mistakes and problems I found. Hopefully that's what you'll find interesting. So first of all, you can't just download a bunch of data off the internet and just say like, this is my training data set. First of all, you need audio and text. So you need to have of course, the audio for a speech to text process. But if you want to supervise tasks, which is what we're doing, you need the associated text. But even that's not enough. You need to discover when each word in the text was said. And the jargon for this is forced alignment or segmentation. Like if you Google like speech recognition forced alignment, you'll find a lot of stuff in case anyone's interested in the exact details of how that works. And we need to do that because we need to split, like audio files, which may be an hour long or half an hour long or even more, into about 15 seconds of audio. This requirement is a little bit odd at first because most people are used to end-to-end deep learning. You put your data in, you train your model on the other, get a trained model on the other side. That doesn't work today because essentially, due to how deep learning training works, essentially you get a linear growth in your memory usage as your time sequence goes on. So anything over about a minute is going to use too much memory at training time. You'll get an out of memory error on your machine learning systems. So we need to this forced alignment process is essentially a necessary evil to produce a usable training data set. And I'll mention that this does use a pre-trained speech recognition model. So some of you may say, hey, is this kind of cheating? You're using a pre-trained model to label your data. You're not actually labeling the data. You're just figuring out when your human provided labels were said in the audio. But it is a little bit confusing because this is in some sense a semi-supervised method. I'll be showing this SQL statement throughout the slide deck. The idea here is that there's a lot to cover, and this SQL statement essentially says everything that you need to know. And I'll be highlighting particular sections in particular slides to elucidate what particular part of the workload I'm talking about. The one thing I want to mention is that here's the motivation for using TPUs or any accelerator for our task. Essentially, that ASR neural network function run on the CPU, that takes 99% of the runtime. So for our case, that was about 20 CPU years. And for perspective, we had, I think, only 32 CPUs available to us for various reasons. So that would take a little less than a year to finish. And with these sorts of data engineering workloads, you're not done after you do the first one. You want to iterate and keep trying new things. So when you take a little over a year to finish a job, you need to find a new solution. In that case, that's using accelerator systems. So the first thing is that some of you may know, introduced in Spark 3.0, there's accelerator aware scheduling. And you might just say, hey, I can just schedule my TPU in Spark, right? And the answer is no, unfortunately. There's a couple of reasons behind this. The first one is that the Google TPU is essentially a software as a service, or you could say hardware as a service over the network. So if you're used to using AWS or Google Cloud Platform, when you allocate a GPU instance, that GPU is part of the computer instance that you create. It's local. It's attached to the PCI Express bus. For the TPU, that's not the case. The TPU instance is a totally separate computer into which you cannot SSH. So because you can't SSH, you cannot create a slave, a Spark slave, essentially, to run jobs on that TPU, on that machine. So effectively, it doesn't really play that well with Spark. But there's more reasons than just that. And like even in the case if you're using GPUs or something else, which does support accelerator-aware scheduling, what you'll probably find, especially if you use a lot of user-defined functions, which is what we do, what you typically find is that the number of CPUs you need greatly exceeds the number of accelerators that you need. So if you just want one single workflow in Spark, like one single Spark job, streaming each task into the other, streaming each stage into the other, that doesn't usually work too well because if you say need like 100 CPUs for your CPU jobs, you're probably not going to need 100 GPUs for your GPU jobs. And there's things you can do. You can do fractional assignment of tasks of a GPU to a task, which can somewhat alleviate that issue. But ideally, if you wanted to use something like GPUs fully in Apache Spark, you have to avoid using user-defined functions, essentially, because those work only on the CPU. And we have a lot of user-defined functions in this case, because we're using a legacy, not quite legacy, but an existing forced alignment code base. Since rolling your own in Apache Spark SQL is not the most fun. But accelerator-aware scheduling does have its uses. One thing I will say is if you're doing data parallel training and you want to do that on an existing Spark cluster, go for it. That's really the original use case that they had in mind. And that's a great use case. But offline inference, it's not so great. So the first thing I want to mention is not actually related to GPUs, but there's so many gotchas and surprises I had on this site. I think it would help a lot of you. So PySpark, writing Python UDFs in PySpark used to be just a big no-no because serialization overheads were too high. So PySpark introduced Arrow UDFs a few years ago, and this solves a lot of issues. But Arrow UDFs are, at least in what I initially expected, were not quite not what I expected. And there's reasons why this is, but essentially, if you look at Arrow, like the fundamental thesis behind Arrow is that it's an in-memory columnar data format that allows separate processes to share memory. And because they all know how that memory is laid out, they can both operate on that memory. So the ideal would be that you have this JVM executor and you have this Python process, and they both act on the same shared memory. Essentially, the JVM does your Spark, your Tungsten, essentially, workload, and your Python does your user-defined function. That's not what happens. In reality, what happens is that you end up doing copies between the JVM and the Python process via serialization, deserialization. And there's good reasons for this. Like basically, you can't. Spark doesn't know the size of your data beforehand, except in a few rare cases. It doesn't have static sizing information, so it doesn't actually know how much shared memory to allocate, which is the reason why it actually does the serialization deserialization process. But the implication of that is that memory usage doubles because you have two copies, one on the Java side, one on the Python side. That's not a lot of fun, especially since there are subtle issues with the Java virtual machine garbage collector, which I didn't know until now, and I hope this helps at least one of you. The Java virtual machine garbage collector, at least as of Java 8, does not return physical memory back to the operating system. So what that means is that at the very least, on your systems, you want to add swap space. I know that some of you may not have that option just because that requires sudo access. You might be using a shared cluster, and maybe you can't convince your DevOps team to do that. But you're going to want to add swap space to deal with possible memory over allocation happening between the Python and Java side. Also, usually you set spark.executor.memory to fill the entire physical memory of your machine. Well, actually, that multiplied by the number of executors on a machine. You want that to fill the almost the entire physical memory, maybe like 90% of it. You can't do that in this case because that does not monitor the memory usage of a Python of the Python UDF. That's using its own separate memory space. So that actually cannot set a ceiling on both of those. So effectively what that means is that you need to be very smart with memory usage if you're going to use Arrow UDFs. That's the short of it. Swap space helps. And just watch out, garbage collection in Java does not return physical pages to memory. So don't be surprised if the first time you make a pipeline, the memory loads in Python are very slow. But we sure know what the problem is. The last thing is that Java can't handle byte arrays larger than 2 gigabytes. And this showed up for me. We have some MP3 files that are almost 2 gigabytes in size. And what that means is that we actually had to reduce batching on the Python side for that reason. We had to set it to 1 effectively, just because if you have almost 2 gigabytes MP3 files in size in total, and you send those over, then try to send those over the wire, Java is going to explode because it cannot allocate a buffer that big. But this is probably what everyone's interested. So, you know, like, what's it like? What's it like using TPUs in a data engineering pipeline? It's a lot of work, is the way to put it. You know, I'm not a Google spokesperson, but I would say overall they got the job done. But it's a lot more manual stuff. It feels like I'm kind of in the MapReduce days as opposed to the Apache Spark days of machine learning plus data engineering. Essentially, you know, we use a TPU v3, a pod of 8 of them. That's the minimum size. We use the Google's Wingbo code base. This is just a machine learning library that they have, which has good TPU support. We use a fairly basic automatic speech recognition model. Don't worry too much about that. That's for those who know CTC. That's very vanilla. You don't want to take a lot of risk when you're using some new software and hardware system. So, waste one with a basic thing. TPUs require you to use Google Cloud Storage as your file system. That's because the TPU is on a separate physical node than the CPU system you're running. So basically what that means is that the TPU doesn't have access to the local file system. So you have to use Google Cloud Storage as your file system, and that causes some issues later on. Also, probably the biggest challenge I had is that TPUs just seem to be prone to crash with a fairly not the best mean time between failures. I don't want to like quote a number because I haven't done exhaustive tests, but my own observations has been that when you're trying to work on 86,000 hours, which is effectively terabytes of data, one TPU job may not fully execute over that because it may crash in the middle. So you need to provide your own restartability logic. And I did add this, but it's challenging for reasons I'll get into later, having to do with batching. It's very hard to make ACID guarantees, things like you won't write out the same record twice if you have to restart a job and restart the job from the middle as opposed to just restarting the job from the beginning. As data engineers, we're very used to doing this. We're very used to our software infrastructure taking care of restartability. Now, I'd say probably the biggest problem that I had is that failures would just happen. What these failures were, they weren't programming errors. They were hard to diagnose effectively because you do remote procedure calls and you get a kind of opaque string error message at the end when something goes wrong, and you can't really diagnose further than that. You can kind of Google it, but I mean, unless you're internal at Google, you're really not going to get a better sense than that one string error message. I have heard that sometimes the TPUs crash when they fill up the disk, but I really don't know. Finally, TPU code can't use the string data type. Surprise, this actually makes a lot of sense because it needs to know static size information. That means you must use integer primary keys if you want to do keyed prediction. And key prediction is the final thing I'm going to get into. So keyed prediction is a machine learning design pattern, which basically acknowledges the fact that when you do machine learning in production, it's not just a machine learning model which has to execute. Usually, we have to join it to other data at the end. Like data doesn't just sit alone. So in our case, we need to join the output of this speech recognition model to the text that we want to align it against. And this is actually surprisingly hard to do because if you want to fully utilize a TPU, and a TPU of pod size 8 has a batch size 1024. If you want to fully utilize that, you essentially have to do this thing called bucketing by sequence length. This effectively does a bucket sort such that even if your data was sorted on the input side by your key, it's going to be stored on the output side by your length, because essentially you want each sample to be of about the same length for full utilization of your processor for microarchitecture reasons I won't get into, and that actually makes things a very big pain, because when you have a batch size 1024. Effectively, what that means is that even if your data is stored on the input, so in our case, it's sorted by this identifier key you can see at the top right highlighted. Both the audio and the transcripts are sorted by that key. When the audio comes out of the neural network process, it's no longer going to be sorted by that key. It's going to be sorted by its sequence length. So actually, you need to do a sort again, at least if you want to do a sort merge join. And I haven't heard people talk about this before. I think the reason why probably is that the output of most most deep learning models is actually a very small output. Like if you just want a cat detector, that's theoretically just one bit of information. So it's very small. So in that case, maybe you can just do a hash join. And if you can do a hash join, that's probably the best thing to do. But in our case, we essentially output logits every 30 milliseconds over 40 tokens. But in some cases, people do like 256 tokens or many more tokens. And for us, that ended up being about 1.5 terabytes uncompressed. So there are two solutions that I came up with other than the hash join. Do what I call map side join. So join what you need before using the accelerator, but that reduces your input bandwidth to the accelerator, and sharding, which you can access via the partition by function in Spark. So you only need to sort each shard. But if each shard is too small, that can actually reduce efficiency. And one of the challenges is that the Google Cloud file system, it's actually not well documented how big a shard needs to be for full utilization. Like, if you use a Hadoop file system, you know that you need usually about like 512 megabytes, maybe 1 gigabyte file sizes. The Google Cloud file system doesn't document that. So there's probably like a 2x speed up somewhere in here, or even more, that would be quite hard for me to get. But yeah, not a lot of people talk about this. And, I do think that if a deep learning software system wanted to be complete, it'd probably need to think about this, in my opinion, since it seems to be something, it seems solvable in software. It's just not straightforward to solve, is the way I would put it. So this is the last slide. What I would say is that, first of all, there's a lot of content in here, and like I couldn't hope to show it all. So all the code is available under an Apache 2 license. If you want it, there's the link. Go for it. My contact info is at the bottom. No promises, but if you have something interesting you want to ask me, or if you listen to this talk and thought, this guy, he totally messed something up, he had a misunderstanding, let me know. I'm very interested. We're all learning new things. And I guess my closing thought is, I think that the ideal for sequence-based deep learning inference, and this is sequence-based specifically, maybe this doesn't matter for non-sequence-based models. I think the ideal is not necessarily to add accelerator-aware scheduling to your accelerators in Spark. I think the ideal is for them to act as an asynchronous queue, receiving input until a batch is large enough to run efficiently. I think that's the ideal setup. And I don't see why you couldn't do this today in Spark. To essentially add a Spark streaming sync, which does this. And I don't see any reason why you couldn't do that. If anyone has thoughts on this, please go and let me know, because then you can say avoid routing a bunch of data to disk, MapReduce style, which perhaps isn't the biggest issue, but terabytes of disk does kind of add up. And that's the talk. Thank you very much.